Now that we've completed our discussion of atomic structure, and we have an understanding of how electrons assemble themselves in a particular atom, we want to move on and start to talk about how that affects the chemistry of each of those elements. We're going to look at how electronic behavior on an atom will affect what kinds of ions it's likely to form and what kinds of compounds it's likely to form. And we'll be working on that really for the next 3 chapters. And this particular chapter is going to focus on ionic compounds. There are 2 major kinds of chemical bonds that we're going to look at in these next 3 chapters. The first that I want to mention, it won't be focused on this chapter, but we'll have to talk about it a little bit, is covalent bond. That's a chemical bond that forms when 2 atoms share several electrons, usually at least 2, usually an even number, but not always. And so that's a bond that's formed by sharing of electrons. And whenever there are 2 or more atoms that are joined together by shared electrons, by covalent bonds, and that group has a neutral charge, we call that a molecule, and that'll travel together as the smallest unit of a molecular compound. The smallest molecules that exist are what we call diatomics, molecules that have 2 atoms. And in fact, in their natural state, there are 7 elements that exist only in that way. For example, we don't find hydrogen atoms in nature. We find hydrogen molecules. And the same thing for nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. An ionic bond, on the other hand, is not formed by sharing of electrons, but from one atom or one or more atoms taking electrons from one or more other atoms. And so what happens in that case is the atoms that take the electrons become negatively charged ions, and the atoms that lose them become positively charged ions. And as a result of their opposite charge, they stick to one another and form what we call an ionic bond. A polyatomic ion, and we've learned some of the names of these earlier in the course, are groups of atoms that are held together by covalent bonds. So they're like molecules, except that in order to fit together, in order to be stable, they have gained or lost some number of electrons in that formation. So they'll have a net charge that's not 0. Some of them can be positive, like ammonium ion, and many of them are negatively charged. One of the most common examples of an ionic compound that we think about quite a bit is table salt, which is made by sodium and chlorine forming a crystal lattice. And when sodium and chlorine are placed near one another, the chlorines have a very large tendency to take electrons from sodium. So chloride ion and sodium ion are more stable than chlorine atom and sodium atom. So the chlorine takes an electron from sodium. That leaves sodium with a positive charge, which means it's going to be more stable, more comfortable, surrounded by things with a negative charge. So in this picture, chloride ions are symbolized with green and sodium with purple. And this, what we call a crystal lattice, forms, giving us each sodium ion surrounded on 6 sides by chloride, and each chloride surrounded on 6 sides by sodium. And so ionic compounds tend to have a very organized crystal structure because of the way those attractions fit together. Something else I want to point out, and we'll make a bigger deal out of this later, sodium atoms are bigger than chlorine atoms, but chloride ions are bigger than sodium ions. Negative ions have a tendency to be larger than positive, the reason why is negative ions are formed by filling up an additional shell, an additional shield, we called it earlier, whereas positive ions are formed by removing an electron shell, removing an energy level, removing a shield. Now, something that we notice is that when atoms form ions, quite often the electrons that will be added or will be removed will give them the same number of electrons and the same electron configuration as a noble gas. For example, hydrogen atom has 1 electron, so hydride ion has 2 electrons. That's the same number that helium has. Lithium atom has 3 electrons, so lithium ion has 2, and beryllium ion, it's 2 plus ion, has 2. That's the same as helium. And the ions in the next column of the periodic table, or next row, I'm sorry, sodium, magnesium, and then aluminum, have the same electron configuration as neon. Oxygen, if we tack 2 more electrons on it, that gives it 10, and it's the same configuration as neon. So atoms will form ions that give them electron configurations that are very similar to noble gases. These ones that have stars on them, they have electron configurations that look like noble gas configurations, but the difference is they also have a D sublevel that's filled that their noble gas that they're trying to mimic doesn't have. So that's a slight difference. As I mentioned earlier, positive ions are becoming positive ions because they're losing an energy level. They're losing a shell, so they are smaller than their atoms, and the difference is even more significant when we talk about 2 plus ions. Not a huge difference in significance, but still more significant. On the other hand, negative ions are larger than their parent atoms. For the same reason, you're filling out another shell and therefore decreasing Z effective on that last electron. Now, ionization energy is the energy that's required to make a 1 plus ion. We've got the textbook definition on the screen there. The energy necessary to completely remove 1 electron from a gaseous atom. And so you'll notice that all of these elements that are in the first row of the periodic table have very low ionization energies. That means it's really easy to remove an electron from them. And that's because that electron we're moving is in a shell all by itself. It's much further away from the nucleus. It's got a very low Z effective because these are the largest elements on the table. And then the ones with the largest ionization energies are the noble gases. And we see not perfect, but a fairly straight line between each alkali metal and its noble gas. Let's focus in on these a little bit and talk about why the trend isn't perfectly linear. These 2A elements have a slightly larger value than might be expected, and that's partly because you're going to be removing an electron from a completed shell, from a partially complete shell, from a completed S sublevel. And so the jump in energy for adding a second S electron isn't as much as for adding a new P electron. So it makes this one a little bit harder to remove than would be expected. And again, we lose our linearity right here as well, and that's because in group 6A, we're removing a paired electron instead of an unpaired electron. And so that changes things a little bit. Let's take a look a little bit at the trends of ionization energy. And this is exactly what we just talked about before. Very low ionization energy for sodium, and a little bit larger for magnesium, and so on as we go across the list. But the second ionization energy is much, much larger. It's about 9 times as large as the first for sodium. So that means it's very, very difficult to remove a second electron. Now for magnesium, the second electron is a little bit more difficult to remove, but only twice as difficult, not 9 times as difficult. We see a large jump, though, when we try to remove a third electron, 5 times as difficult. And then we see a similar trend, aluminum, higher electron ionization energy, 3 times as high, not even twice as high. And then again, 4 times as high. So this huge step comes at the noble gas configuration. It becomes much more difficult by a factor of at least 3 or 4 times to remove from a second shell from an additional energy level. And that's why we see these trends in ionization energy here. The opposite of ionization energy is electron affinity, how much energy is involved in putting an electron onto an atom. And something to notice here is that these trends are negative. We get energy back. It's an exothermic process for most atoms to accept an extra electron, especially, look at here, the halogens. They have very large negative electron affinities. It's an exothermic process to place an extra electron onto these. And then golds is surprisingly large as well. But look down at the bottom of the table. Several of these that are shown as 0 actually can't be measured because it's an experiment that can't really be conducted. And the theoretical values are positive numbers. It's would be endothermic to place an extra electron on some of these. And many of those are noble gases, and also the S2 column, the magnesium beryllium column, the 2+ column of the periodic table, column 2A. You're putting an electron into a new sublevel in those cases, and it's a positive and endothermic amount of energy involved. Now what we're going to notice is that main group elements, ones in the first 2 and the last 6 columns of the periodic table, tend to undergo chemical reactions that leave them with 8 valence electrons. For example, sodium will give up an electron. The electron it gives up is a 3s, and what's left is the highest energy level is now level 2, and there are 8 electrons on it. We're left with a noble gas configuration, or 8 valence electrons. On the other hand, chlorine has 7 valence electrons. If it absorbs an additional electron, this one will become full and we'll have a chloride -1 ion. Now what we're showing here is what would happen to get chlorine +7, and that's not a normal state because removing 7 electrons is very, very difficult. But if I had you back in chapter 4 count out the oxidation number for chlorine on a perchlorate ion, you would get +7. So this is not an entirely ridiculous way of looking at chlorine. And we only have a few slides left. I'm going to put those in a second video. They may take a little bit longer to talk about as we talk about some of the energetics involved in bonding.